the black hole. It's one of the most fascinating objects we can find in the universe. It is described by the mathematics of the general theory of relativity, proposed by Albert Einstein in 1915. Its description is related to the concept of mass being compressed beyond a certain limit, resulting in some of the most intriguing consequences in physics. You often hear about many of them, mainly related to gravity. But you don't often hear about electricity in this context, so what about a black hole that is actually electrically charged? And here, we're going to take a look at the mathematics behind this type of black holes by analyzing something we call the Reissner-Nordstrom metric from a different point of view. Because it may take us to a beautiful journey through mathematics. And I really hope you enjoy it. We're going to start with the most basic concept about gravity. Two masses with the same sign attract each other. This is the reason we have weight. In 1687, Sir Isaac Newton mathematically modeled this behavior with what we now know as Newton's law of universal gravitation. On the other hand, two electric charges with the same sign repel each other. In 1775, Charles-Augustin de Coulomb modeled this behavior with his inverse square law for electricity, and this is when we started to model the behavior of two bodies with mass and electric charge just by adding up these two forces together. Thus, if we know about their masses, their electric charges, and what's the distance they are apart from each other, we can plug them into this equation to get the total force felt by the two bodies. So that if it's positive, the force would be repulsive. And if it's negative, we say it is attractive. For those that are unfamiliar with electricity, we measure electric charge in coulombs. And for those that are unfamiliar with everything else, we measure mass in kilograms. All within the International Metric System. Although these two laws are included in what we call classical mechanics and classical electromagnetism, and they are a good approximation only within a certain range of values, we're going to use them to get to a key concept. The concept of mass units. Because notice that the same way we can translate centimeters into inches, we can translate coulombs into kilograms. It's a change in the unit system. So if Coulomb himself would have chosen this way to express the electric force, the two laws would look almost identical. Except they have opposite sign. Yet by doing this change in the unit system, everything can be expressed in terms of kilograms, no coulombs anymore. So yes, it would be confusing if we wouldn't know the type of each mass beforehand. But it also would be dangerous because we could easily make a mistake by adding these two types of masses together since they have the same units. Luckily enough, Coulomb didn't express his law in terms of mass units, so it is less confusing. And we never add up electric charge and mass together, right? The truth is, we can still fall into a similar trap. In fact, this is in the heart of the assumptions in the Reissner-Nordstrom metric derivation. But before saying something about that, let me introduce the main character of this story, the metric tensor. Do you know what it is? Let me show you. Do you know what a vector is? These little arrows you often see in physics textbooks. It's a useful way to represent information in a visual way. Now, imagine two vectors, and imagine the shadow of one of them projected onto the other. This quantity here is related to an operation we call dot product. It is everywhere in math and physics. And do you know what a reference frame is? It's related to the way we numerically represent vectors. And to explain something about the dot product, you have to know relative to what reference frame vectors are defined. The first time you know about it, you learn it is a basic operation. Take the first component of each vector, multiply them together, do the same with the second components, and add them up. Now take this quantity, divide it by the length of the vector we are projecting onto, and the result is exactly the length of the projection we are interested in. Easy, but that's not the entire story. Because notice that since a reference frame is a completely free choice, we can just change it. And by doing so, notice how these numbers change. And most importantly, notice how the result of this operation also change. However, this length never changed because the vectors are the same with respect to each other. Therefore, if we want this number to represent this projection, no matter what the reference frame is, we have to do something else. Yes, enters the metric tensor. This is a way to say that a matrix multiplication would be now involved in the operation, so let's write the first vector as a row vector. This metric tensor, here represented by a 2 by 2 matrix, is related to the basis vectors that define a reference frame. Let's call them x hat and y hat. We build this matrix by taking the dot product between these vectors, which in this case, where they have a length of 1 unit and the angle between them is exactly 90 degrees, the values of the matrix components are these. And if we now change the reference frame, then they adapt. See? Now, by introducing the metric tensor in the operation, look what happens with the value of this seemingly innocent quantity. It remains invariant. Quite practical, right? The main takeaway here is to let you know about this object we call metric tensor. You can think of it as a matrix that contains information about the reference frame, and a possibly new concept for some of you is that we say it is defined for each point. In this case, it is the same everywhere. I mean, these numbers are constant across the entire space the reference frame is describing. But again, this is not the entire story, because they can actually be not just constants, but functions of any variable, even of the position itself. And if that's the case, depending on the form of the functions, we say the metric tensor describes a curved space, which means that the basis vectors themselves are not constant. Remember how we built the metric tensor? They change from point to point. Don't worry if you feel it is weird, because it is. It took years to geniuses like Gauss, Riemann, or even Albert Einstein himself to develop these ideas. And it takes years to us to get used to these concepts. Here we have been working with a two-dimensional metric tensor for simplicity. In the context of the general theory of relativity, these are four-dimensional tensors, like the Schwarzschild metric tensor or the Reissner-Nordström metric tensor. I hope they feel less unfamiliar by now, because what you are actually seeing on screen now are the specific functions that make this metric not constant, remember? So let's see how we can get here. And to do so, we first have to talk about electromagnetism and the electromagnetic tensor. Let me briefly show you where it comes from. This is James Clerk Maxwell. His name is associated with one of the most important pieces of mathematics in the field of physics. This set of equations we now call Maxwell's equations. They talk about electricity and magnetism. They are a summary of observations about nature, like the familiar interaction between two charged bodies. Now let me tell you one observation that is probably less familiar for some of you. Did you know that if we have two electric currents flowing in two different wires, we observe a force that appears to make them repel or attract each other, depending on the directions of the currents? So that if we take control of one of the wires and start switching the current on and off, someone over here would notice what you are doing over there. This specific setup would be inefficient, but this is what wireless communications are based on. The information about us switching the current on and off travels in what we call an electromagnetic wave. And since it's information and it travels fast, it was a matter of time to start building communication systems that are based on this phenomenon, which is also summarized in these equations.
Who's have a clear to land? Ah, short approach, my fucking favorite. That guy know he was talking on the radio?
They are beyond useful. At the moment you start learning about electromagnetism, you find that it can be conveniently expressed in many different ways. And this one in particular is expressed in terms of a tensor, which is the language of the general theory of relativity. If you want to know how to get from the electromagnetic tensor to Maxwell's equations, there is a video linked in the description. Don't worry if it's beyond your knowledge. All you have to know is that it comes from the study of electricity. And everything related to relativity comes from the study of gravity. One of the main goals of these videos is to talk about the Reissner-Nordström metric, which is an attempt to use our knowledge about gravity and electricity to describe an electrically charged black hole. So let me introduce the second character of this story, Einstein's field equations. It's our best mathematical description about gravity so far. It talks about how energy is responsible for the curvature of space and time. It means, given a specific distribution of energy, we can calculate how it curves the reference frame itself. Remember how this curvature was related to a metric tensor? Because it's one of the key pieces of information we can extract from this equation. Let me give you an analogous example. Remember how you solve for x a simple equation? If a function of x is, let's say, equal to 0, then x would be equal to 1. In a similar way, if we know how energy is distributed, which means we know the values of the stress-energy tensor, we can calculate the metric tensor that satisfies this identity. For example, if we assume a body with all its mass concentrated in one point, the metric we find is the one Karl Schwarzschild found, incredibly during the World War I while serving in the army. He assumed the right-hand side to be 0 and the left-hand side to be just r, and analogous to a function of x, we can see r to be a function of g, a metric tensor. And the left-hand side to be 0 means that there is no energy in the region under consideration, just empty space. Thus the term vacuum solution. He did the math, which consists in solving a set of differential equations. And this was the result. We call it the Schwarzschild metric tensor in his honor. It describes the surroundings of a non-rotating black hole by assigning a set of numbers to each point in space depending on the distance to its center and the amount of mass inside. And one important thing to remark here is about these two numbers. Outside the black hole, this is negative, and this is positive. Inside a black hole, this becomes positive, and this negative. In fact, this is how we differentiate between the inside region and the outside region. And this happens when this term is greater than 1. Which in turn happens when this term is greater than this one, the distance to the center. And the term event horizon refers to the limit of these two regions. It implies there would be a spherical region in space, where once inside, you would have to go faster than light to get out of it. Something we know it's not possible. Its radius depends on how much mass is inside this region, with all mass concentrated in the center. No other distribution of energy elsewhere. On the other hand, if we add electric charge, and this time we say the field stores energy, we have to specify it in the right-hand side of the field equations. This is exactly what Hans Reissner and Gunnar Nordstrom did by setting the right-hand side of the field equations equals to something we call the electromagnetic stress-energy tensor, which is constructed out of the electromagnetic tensor. This is what Hans Reissner and Gunnar Nordstrom assumed. And they did so because of this equation. which says that mass and energy are equivalent. We know mass creates gravity, and in the context of electromagnetism, we say energy can be stored in the electric field. Therefore, it must contribute to the gravitational field. It's energy after all, and units are the same. They did the math, and this is what they got: the Reissner-Nordstrom metric tensor. It is different from the previous metric tensor in this term, which is what depends on electric charge. We put the event horizon at the distance this term equals 0. And in this case, it's a quadratic equation with two solutions. Two distances at which this term equals 0. So that if we use the metric tensor to calculate actual numbers, in this region, this would be negative, and this positive. If we cross the first horizon, they switch their sign. And if we cross the second one, they switch their sign again, as if everything would be back to normal. These two distances depend on mass and electric charge, so that if we increase charge, the inner horizon would grow and the outer horizon would shrink according to these equations. If we keep increasing electric charge, the two horizons would eventually overlap. And a bit more of charge would make them disappear, since in this case, they would be complex numbers because the value inside these two square roots would be negative, leaving a naked singularity in the center. Although according to Wikipedia, a body with excess of electric charge could not collapse to a black hole. Do you remember how we can convert coulombs into kilograms? This is the conversion factor. It is approximately this number. And when multiplied by electric charge, it leaves you with a total in kilograms. Analogously, we can do the same with the electric field, which when multiplied by this factor, it leaves you with a total of meters over seconds squared, the same units as a gravitational field, so I call it intentionally G. But it is still the electric field, not the gravitational field, and the same conversion for the magnetic field. So, this is where Reissner and Nordstrom originally started. Although this is the tensor they had into consideration, we're going to keep all the terms. And we're going to write this in terms of the new substitutions. Multiply both sides of the electromagnetic tensor equation by the same amount. Distribute it in the right-hand side. Replace with these identities. Multiply by 1 the right-hand side of the field equations. This cancels out. Rearrange and distribute. Let's give this a new expression. And here I'm using the same letter, just with a different color, but notice they are not equal. Use this to replace here and here. Write the simplified tensor so that we don't need this anymore. The Reissner-Nordstrom metric tensor is the metric found by solving the field equations when considering the electromagnetic field. Its components depend on mass and charge. And this is the total mass of the body. It's a combination of the mass concentrated at the center and the one responsible for the field. And the term irreducible mass is a combination of these two masses as well. Let's write the total mass in this way for a moment. So here is the thing. If we forget for a moment about the substitutions, from what's left, it's easier to ask the following question. Can we just say this is the gravitational field and not the electric field? Because the answer to that question is yes. It turns out that the only requirement for the field is that it has to be equal to a constant divided by a distance squared. We say this constant is equal to this because this way we can relate it to Coulomb's law, here hidden behind the substitutions. But it's just as legal to consider the negative version of it, which is Newton's law. It would solve the field equations as well, but with an important catch. This time, the mass responsible for the field represented by the tensor would be equal to the mass concentrated at the center of the black hole. Now the square roots are 0 and the total mass simplifies to this, leaving a black hole with one event horizon with a radius half the size the one we find when we consider the vacuum solution, and with a total mass even bigger than what you started with. So here's the catch. Both are two different descriptions of the same phenomenon, and they don't match. Should we take into consideration the energy stored in the field? This is something Karl Schwarzschild himself didn't do. Perhaps we shouldn't. Not even for the electric field. Otherwise, the resultant metric always describes a region of space where the singularity is not in the future, something we call a naked singularity. It happens along with some other peculiar predictions. For instance, the metric would allow you to enter a black hole and then get out of it. It doesn't help either. We know how to solve the gravitational case, in which the energy is inside the black hole. So, a natural question is, why would the electric case be different? I hope you enjoyed it, and see you next time.